Okay, so the ball's in your court to ask questions to prep for the exam on Wednesday. Okay, have a good day. This one here? Okay. So this is asking to use the R0 and R1 lines in the HCl spectrum above to determine the rotational constant for HCl 37. Okay, so first of all, well, first let me ask you, what are the things in this problem that you wanted more information on? Like if you were like trying to send me an email on this, and you know that I need a specific question so that I can answer you quickly, what are some questions you have about this? Let's start left to right. R0 and R1, do you know how to find those? You do? Okay. Which side are they on? R's are on this bigger side, the higher wave number side. So this is the higher wave number side. So this has to be the R branch, and this is the P branch. This is a diatomic molecule, so no Q branch. Okay. So there's no Q. Okay. So this is the HCl spectrum. No, nothing confusing about that. Determine the vibrational frequency. Oh no, we're down here. Determine the rotational constant for HCl 37. So do you have any questions about that? What do we see in this spectrum? You see the little doublets? Yeah. So those are it's the same molecule, but the only change is the chlorine mass. So we have the isotopic pattern here in the infrared. So which is the taller peak? How do y'all know that? How do you know that? Yeah, because of the weight, exactly. So we've got chlorine here. And what is the mass of it? 35.5. Okay, so that's the average mass. And so it's, x times 37 plus 1 minus x times 35. And that's equal to 35.5. So you could figure out what x was and solve for the ratios. But all I need to know is that it's closer to 35. So 35 is the most abundant one. So 37 is the smaller peak. And so this is R0 and this is R1. And we're going to use the smaller numbers. Does everybody check my math? Is that what you guys did? Yep. You use the smaller numbers because that's we're looking for the 37. Yeah, the smaller number, the 37s. Okay. So this difference, 2923.7 minus 2904.1. 6. Let's see. 13 minus 4 is 9. Is that right? Okay. 1, 0, 0. So 19.6 wave numbers. So here's where I get to Hamlet. What do I mean by Hamlet? 2B, 2B or 4B. This is an infrared spectrum, and so this is equal to 2B. So B is equal to that divided by 2. So, do you know which one it is? see, yeah, 9.80. Okay. All right. So that's how you find B. Also, let's look at, notice how there's really no difference in the spacing as we go out between 37 and 35. Right? 37 and 35 are always next to each other by the same amount. Okay. So there's no difference in bond length. There's a slight difference in bond in the mass, obviously the reduced mass. But the reduced mass is really governed by the hydrogen. So there's really not much difference in the structure of 37 and 37 HCl and 35 HCl. There should be a slight change in the reduced mass, but in terms of the bond length should be the same because it's the charges on the nuclei that give you the bond length. Okay. What about the vibrational frequency? How did y'all find that one's? This says, it tell you which ones to use. And the reason I do that is because I want you to, because there's a many different ways you could calculate it. You could take R0 and P1 for 37, or you could do it for 35, or you could do R1 and P2. Like you could calculate any of those symmetric peaks and calculate the vibrational frequency. So I have to tell you which one I'm using for my answers. Okay. So we're saying use R0 and P1. So that's these two to find this right here. Nu 0. So it's right in the center. So you're just averaging those two numbers would give you the vibrational frequency right in the middle. It's kind of interesting. This is the spectrum of the fundamental of that vibration, and yet there's absolutely no peak where Nu 0 is. We have the rotational structure on both sides, but there's no peak where Nu 0 is. So we can't even get just a straight vibrational excitation without also getting the rotation, because the vibration of this molecule doesn't have any angular momentum associated with it. So we have to change the angular momentum because light has 1 unit of angular momentum. So we have to have a rotational change and a vibrational change when there's a diatomic molecule. So we take the average of those two and we get one of these. I don't remember which one it is. But do you remember? We'll just do it. So 2904.1 plus 2863.0 divided by 2. Who has a calculator? You got it? Okay. It's 2883. Okay. Thanks. And then I'm just picking a peak over here. You know, which one is this? So we go up here, 2821.5. 20. This one right here. So this is P1, this is P2, this is P3. So that's P3. So we would get rid of the P2s, or the R3, and then we got to decide which isotope it is. It's the taller one, and so it should be HCl35. Yay! Okay. Now, what's interesting about this? We're not gonna do this calculation, but I want to connect this to, you know, current events, measurement of the global temperatures, and things like that. So when we did the particle in a box, the intensity of rotation in the book, it's one of the chapters. There's the solution of the transition dipole moment integral for the particle on a ring. And when we solve for that, the intensity associated with that transition is a constant. It's like 0.25 for all of the peaks. So these peaks don't have a constant value, do they? They go up and then they come back down. They go up because of degeneracy. So the intensity from nu zero, all these rotational lines go up because the degeneracy is 2j plus 1. You know, the Boltzmann factor, G of j is equal to 2j plus 1. But we also have the Boltzmann factor, the temperature piece, and it goes down, right? It starts out and it's an exponential drop. E to the minus E sub j over kT. So the maximum here moves around with temperature. So we could model the intensity of these peaks, how they go up and then come back down by changing the temperature. So you could, this is a fun thing I do in the graduate thermo class, is that you could basically model a stick spectrum or even the whole spectrum based on temperature. And you could change the temperature until they match. And when they match, you've got the temperature of the gas. So that's pretty cool. You didn't touch the gas, you didn't use a probe, you didn't do anything. You just shot light through it, modeled it, and said, oh, I now know the temperature of that gas. So we can send a satellite up and look at the sun. That's our source. Look at the infrared absorption of all of the gases in the atmosphere, model the rotational structure, and get the temperature of the atmosphere. We could fly that satellite around the Earth and get multiple measurements of the temperature of the atmosphere using the sun as a source. So that's pretty neat. And it was using the rotational lines in this Boltzmann distribution. Not on the test, but really cool. Since we've got this nice pattern of intensities, it might as well, mention that at least. Okay. And then we can solve for the bond length. I just want to make sure y'all have other questions before we do that. Yes.
I have a conceptual question.
Good.
It says the molecule must possess a dipole moment.
That's right. A net dipole moment.
But for pure rotational scattering, if the light interacts with polarizability, then no dipole needed?
Yes.
You explain the difference.
Yeah. So we're doing so for scattering, like we could have a nitrogen molecule and its electron cloud. And so since every molecule has an electron cloud, every molecule can scatter light. So there's no permanent dipole needed. For direct absorption of light, we have this oscillating electric field in light. And so for HCl, we need that permanent dipole so that we, when it's rotating, that dipole's oscillating when it's rotating up and down. And so then if it's rotating at the right frequency with light, then it can absorb and get a kick and go faster. Okay. So that's needed to absorb the light, but not to scatter the light. So scattering can take place just with oscillations of the electron cloud. They don't have to be polarized. Now, Rayleigh scattering is responsible for the sunsets being orange or red and the sky above us being blue, because it's a function of frequency. The scattering efficiency is a function of frequency, and so blue light is scattered more efficiently than red light. So when we look up, we're seeing light that's scattered 90 degrees very efficiently, and the red light's not scattered, so it goes through the atmosphere. But then when we're looking at a sunset, we're looking at the red light because the blue light's been scattered away. So it depends on viewing angle. If we're looking at the sun, 90 degrees, we're looking up at the sky, the sunlight that's scattered down is blue, and the sun that's not as scattered as efficiently as red. But if we're at a sunset, then it's this way, and we're looking at the red light, not the blue light. Okay. Are y'all good with the propagation of uncertainty? Not so much? Yes? No? I see some shaking heads. Okay. So here's an example. Rotational constant is measured to be 10.75 plus or minus 0.25. What's the CV? Okay. So coefficient of variation, That's CV. So go through that online lecture on the propagation of uncertainty, so you understand the terms and understand how to do these calculations. Let me just pull up those notes real quick. Okay. Here it is. Close this out. Open the other one. Yeah, okay. Okay, so this is definitely no card bait. Let me put a scratch paper in here. Okay, so if we have, let's say 1.26 plus or minus 0.03, what's the relative standard deviation? That's equal to S over X bar, and we're assuming that this is X bar, that's the average value, and this is S. And so it's 0.03 over 1.26. Can you be my calculator? Okay, good. So that's the relative standard deviation. And so that's the thing, when you're looking at 0.03, that's, that sounds, I guess that sounds okay, but we really don't know if that's good standard error or not, because we don't know what X bar is. So relative standard deviation is what's your uncertainty relative to the value that you measured. So take the ratio and get the relative standard deviation. The CV is the coefficient of variation, and it's that times 100%. Okay, so this times 100% is 2.4%. So that's pretty good. So our measurement of 1.26 has 2.4% uncertainty. So that's not bad. To take this number then and multiply it by another number, let's say we have y equals mx and b is equal to 0. So it's a linear thing, but the intercept is 0. And our m is 1.26. Our average x, or let's see, that's this x bar. So let's use that. So this is 1.26. And m is, I don't know, let's say 47.3 plus or minus, say 4.7. So I'll give it 10% error. Okay. So what's the uncertainty in y? We can calculate y easily. Y is equal to 47.3 times 1.26. So please calculate that for me. 59.6. Okay, and so what we need to know for this propagation of uncertainty is this, it's plus or minus what, right? It's not 0.03 because that's the uncertainty associated with our X value. It's not 4.7 because that's the uncertainty associated with M. We need to figure out what the uncertainty is in our result. And so this is where we end up with this, how we use this table. So which row are we on? So even if you wrote this on your note card, or if I handed it out to you, if you don't know how to use it, it doesn't do you any good, right? So you got to figure out, is it a log or an anti-log that we're doing? No, it's not. Is it an exponent? We're not doing anything squared or to the cube, or square root is a 1/2 power. Okay. So it's not that. So it's sum or product. It's y equals mx, m times x. So it's a product. Okay, so we're using the second row here. And this is the uncertainty equation that we need to use right here. Okay. So I'm going to use S just so that you get, is equal, S of y is equal to y times the square root of RSD m squared plus RSD x squared. So see, it's the sum of all of those RSDs squared. You take the square root and multiply by y, and you get S. Okay. So let's figure out what our RSDM is right here. So that's 4.7 divided by 47.3. 59.6 times the square root of 4.7 over 47.3 squared plus 0.03 divided by 1.26 squared. It's a little tedious, lots of little numbers in there, but it's not too bad. Do it in parts. We've already done this one. This one was 0.024. This one, if you look at it, 4.7 over 47, that's 0.1. Yeah, so this is 0.1. I did that on purpose for myself, squared. The square root of that, multiplied by 59.6. I need a better calculator.
6.1.
It's going to be six. I'll just keep 2 digits, 6.1. Okay. So 59 plus or minus 6.1, or 59 plus or minus 6. So that's our SY. It's pretty close to 10%, isn't it? And that is enough, probably, in many cases, if you were to be given a problem like this, this is equal to 0.1 or 10%. When you multiply 0.1 by 100%, I get 10%. This is the worst uncertainty, right? This one was 2.4%. This one is 10%. Your worst uncertainty is going to ruin your result. It's going to carry through. So if any of your uncertainties in your problem, if it's multiplication and so on, the worst one is going to be the one that shows up in the end. So you can look at this and see which one of these is going to be a problem. This is 10%. This is 2.4%. So this propagation of uncertainty isn't just an exercise in calculating numbers. It sort of tells you that in the precision of this instrument, my M is screwing me up. Because no matter how precisely I measure my X's, when I multiply by uncertain M at 10% uncertainty, my result is going to be 10% uncertain. So I need to do a better calibration and get a better slope with a better precision so that I'm not ruining the precision in my result. Okay. So that's propagation of uncertainty. This is how you use it. If we were to do the sums and sums, we would just, instead of squaring the RSDs, we just square the uncertainties themselves. Yes.
How would this like instead of on like an exam question? Like how does this
Well, that's what that RSD one there. So let's go back to that homework. It was like the CV and the RSD, just asking what those were. So you've got, let's do one. I guess I can erase. Let me just create another slide. Scratch paper. Okay. Yeah. All right. So let's say we've got B is equal to 10.0 plus or minus 2.4. And we solve for, we want to know what the uncertainty is in the bond length, right? So R is equal to the square root of that 16.8 long set of numbers. Do y'all have that? Anybody have that available real quick? Go ahead. Okay, let's just go to 857. Okay. Okay, and that was wave numbers, um, angstrom squared, grams per mole. Okay, and then in the denominator we had the reduced mass. Golly, what is that? We're gonna say mu is equal to. I'm gonna make the math real easy. 16.857 grams per mole. Look at that, smart man. Okay, so mu is 16.857 grams per mole. Okay, and then our B value is 10.0. Okay. So we may end up with a really wonky, tiny little bond length, but that's what we're going to have. So what does that end up with?
0.3?
Okay, tiny little bond length. But anyway, it is what it is. That's what we got because our reduced mass is so big. Okay, and so that's our bond length. Plus or minus what, right? So we don't know. But we know that plus or minus in this. Well, this is products, right? It's a multiplication and division, and so we would go back to our little sheet. But in fact, it could be seen as this one right here. So we've got a number raised to the 1/2 power because of the square root. So let's use this one. You get the same result if you use the products, but we'll see. But anyway, so we got to have this is in our example. This is B, and this is SB, and this is 1/2 for the square root, and this is our 0.32. Does everybody see the parts? Yeah. So let's go ahead and do that. So the uncertainty in bond length is equal to the bond length times X times SB over B. So this is an example of the calculation. So 0.32 angstroms times 1/2. The 1/2 is because it's this X right here. It's the square root. Okay. Whatever power you're raising it to. You could have just as well put this in parentheses and said 1/2. So it's that power that we're using. And then it's 2.4 over 10. Okay. 0.03. 3. Okay. angstroms. So that's how you would calculate the uncertainty in your bond length if you knew the uncertainty in your B value. And you get the uncertainty in B value from your regression analysis. So you will do this exact calculation on the carbon monoxide lab. You'll get an ANOVA output and it'll say, it'll be their B value, that row. You'll have your B value and the next column is your uncertainty. You do this calculation to calculate your uncertainty in R. So that's why this is on this test to get you ready for that lab, because that's when you're going to need to use it. Okay. I haven't looked at I take the tests from previous years and kind of modify them and so on. And last time I took it from 33 questions up to 50 by adding a whole bunch of symmetry ones. That I think in general that helped everybody, but I wanted to ask if you guys want me to do that again. Just add a lot of little short questions so we get the numbers up to 50. I don't think people are having a hard time finishing with 50 questions because they're like, you know it or you don't. But what do y'all want me to do? Leave it at 33 or bump it up to 50 with symmetry, point groups, hybridization orbitals, and so on? I just want to really hammer that information because it's so foundational. Bump it up. Okay, that way you'll have more opportunities for points and things like that. Okay, so I'll do that.